I think we'll just begin the class. So, am I audible? Ishan, Sukanya, yeah.
Yes, ma'am. Yes, ma'am.
Okay. So, okay, let's begin. Yeah. So, hope my presentation is also visible.
Yes, ma'am.
Yeah. So, let's start. So, welcome to week 5 of experimental biotechnology course from NPTEL. Course is offered by Professor Vishal Trivedi from IIT Guwahati, and I'm one of your TAs, Sumati Raviraj from University of Hyderabad. So you can mail me at this mail ID, and the contents of this presentation or anything regarding chromatography or gel filtration, you can go through the link if you need like further more details. Since we will be discussing only relating topics to this week's assignment, you can check out the entire PDF for further contents. So this week basically it's mostly about gel filtration. So some of the slides might be repetitive, but we'll go through them because we have to go through all the questions. And then in the end, maybe couple of questions you guys can answer on your own based on whatever explanation has been given. So, coming to gel filtration chromatography, it is also known as size exclusion chromatography or SEC. So, the basic principle, just a second, yeah. Yeah, so the basic principle behind the gel filtration chromatography is based on size and separation based on the size and shape of your proteins. So here we have a stationary phase which consists of beads. These beads are made by cross-linked polymers like Cefidex or Cephirose or Superdex. So these are the materials that are used to make these beads, which have certain pore size depending on the material, depending on the type of the concentration that has been used in specific beads. So since they cross link, so similar to like how your agarose or your polyacrylamide cross links and has pores in them. So this is also a similar concept of cross-linked polymers having defined pore sizes. So these beads have defined pore sizes when a protein mixture is loaded onto the column. Large proteins are too big to enter the pores. So what happens is they go to the gaps and they just pass through the column. So they move quickly around the beads and elute earlier. That is, they elute first. And the smaller beads, which can enter the pores, will pass through all the pores, through all the beads present in the column from top to bottom. So therefore, their uh, travel time is more or retention time is more, and they get delayed while elution, and then they elute later or elute at the end. So basically separation is solely based on the molecular size, that is the hydrodynamic radius, and not any type of chemical property like charge or hydrophobicity. So it is only because of the size difference in your proteins, whether it's your native form, your different proteins, or your unfolded proteins, linear protein, anything will get separated based on the size and shape of it. So, the factors that do not matter here are polarity, hydrophobic nature, and isoelectric point. So, theoretically, polarity is important in case of adsorption and partition chromatography like TLC and HPLC, and hydrophobic nature is made use in case of HIC and not in gel filtration. So the isoelectric point. So Pi is not crucial here. Pi plays a role in your ion exchange chromatography, both cation and ion exchange, because depending on your pH changes and pi of your protein, it will attain a positive or a negative charge based on which you can separate an ion exchange and not in gel filtration. So basically, the major factor here is size of the protein in simple terms. Larger proteins elute earlier and smaller proteins elute later. So this is why the gel filtration is also used to estimate molecular weight of the proteins, nucleic acids, or polysaccharides. So like I said, similar to your polyacrylamide or your agarose, where you use your size to separate it, and you can also identify the molecular weight of your proteins. So here also you can estimate the molecular weight of proteins, nucleic acids, or polysaccharides. So what are the applications of it? So determining the molecular weight of an unknown protein by comparing it with the standards. So in your gels, when you run them, you will have a ladder, that is a marker which has standard protein weights which resolve at particular uh, position in your gel. So similarly here you need to have your standards, that is your known molecular weights which will elute at particular volumes or at particular retention time. So based on that standard you can find out the molecular weight of your unknown protein as well. Then is buffer exchange or desalting. Since small salts can enter the pore and they will be delayed, while proteins will come out first. So, based on your salting in, salting out, desalting, your buffer exchange, you can change it and make your proteins elute out at different times. Then, purifying protein complexes without altering their structure, since it's a gentle non denaturing method. So if you have native forms of your proteins, or if you have different proteins which are in a complex together and you want to elute out the complexes, separate out them, purify them, you can also use this to do that. Then studying oligomeric nature of the protein. So oligomerization of the protein is nothing but when many monomers of a protein join to form different oligomers, which is like more than one monomer together. It can be a dimer, trimer, tetramer, nanomer, pentamer, hexamer, anything. So these different oligomers of proteins will also elute out at different fractions because of their change in the size and shape. So you can also study the oligomeric nature of the protein. Then to explain in simple words, like this is an example or an analogy. So you can imagine a ball pit with different sized holes. So big basketballs have larger proteins, are larger proteins that cannot enter the holes and they just roll down fast. But small balls like marbles are smaller proteins, so these marbles will fall into the holes and will take longer time to get out. So the balls are separated only by size, not by color, not by texture, not by weight, nothing, only and only solely size. So in case of gel filtration chromatography, the size of the protein is the one factor that determines the separation. So next, in case of gel filtration, larger proteins elute first, like we discussed. So because they can't enter the pores of the beads, like the basketballs, they just roll over when there are holes which are smaller than the size of the basketball. Similarly, your larger proteins will elute out first, so they take the shortest path. So if you have a case where you have different sizes like 65, 25, 15, 5 kilodalton, so which will elute first? Your highest among all these is 65. So your 65 kilodalton is the largest one, so it will elute first, so it will come out first. So this technique separates protein based on size and shape. The stationary phase is made of porous beads, cephalics, superdex. Molecules travel through the column, but their path depends on whether they can enter the pores of the beads or not. So your proteins will take two paths here basically, depending on their size and depending on the size of the pores in your beads. So if your protein size is bigger than the size of your pores in the beads, they will take a different path. They will take the shortest way, that is passing through the gaps and flow out. And if your protein is smaller than the pores, it will definitely enter into the pores of the beads and it will take a longer path through the beads from top to bottom. So the basic mechanism, like we said, is too big to enter into the pores are your large proteins. In this case, it is the protein which is of 65 kilodalton. So they move around the beads and then they take the shortest path through the column. As a result, they elute earlier. Then small proteins like 5 kilodalton, 10 kilodalton, 15, 25 kilodaltons are small enough to diffuse into the pores. So this means that they get delayed, and because they spend more time in traveling inside the beads, the smaller molecule will take longer time and their illusion or coming out will be delayed. So basically your order in case of this will be your 65 first, which is too large to bypass the pores. Then your 25 kilodalton, which can partially enter the pores. So if it is in between, somewhere close to the pore size, it might enter the pore, it may not enter the pore. So depending on the size difference. Then 15 is smaller, so it will enter the pores more deeply. And the last is 5, it will enter almost all the pores in its path and it will take the longest path. So this will be the order in case of an option like 65, 25, 15, and 5. So the key concept to remember here is gel filtration separates based on protein size, not charge, not hydrophobicity. Then larger proteins elute first and smaller proteins elute later. So you can see these are the cross-linked polymer beads. So you can see depending on the material, depending on the concentration of the material used, you can have different pore sizes in the beads. So these are beads with larger pore size, these are beads with smaller pore size. So if you use a particular bead like this which has a larger pore size, so most of your proteins will enter into the pores, into the bead. But if you have proteins or complexes or oligomers which are much larger than the pores, they will be outside your bead. So they will just cross your bead or flow outside your bead. So the exclusion of large sized molecules and inclusion of small sized molecules in the pores will take place. So basically if it has to travel from here to here, your larger ones will just take the shortest path. It will just flow over your bead and it will go down. But if it's smaller like this, then it will enter into this pore, then it will enter into this pore, this pore, this pore, this pore. So by the time it crosses all the pores and it comes, the time will be more and your retention time will increase. So next is hydrophobic interaction chromatography and surface area. So proteins are made up of both hydrophilic and hydrophobic non-polar amino acids. So normally your hydrophobic amino acids are buried inside the protein core, but under certain conditions like partially unfolding or local surface exposure, the hydrophobic patches are exposed. Like I think we discussed about this in the last session. So this is just like a recap of it. So in case of HIC, the stationary phase is hydrophobic ligand, butyl octyl, and phenyl groups attached to the agarose and sapphirose beads. So when a protein in the solution is applied in high salt buffer, water molecules are withdrawn from the proteins which is salting out. And then you have larger hydrophobic patches with stronger binding. So here in this case, your illusion is by gradually reducing the salt concentration and your hydrophobic interactions. So it's just like a comparison, like how different it is from your uh, gel filtration, because this does not depend on any hydrophobicity. Hydrophobicity, like I said here, so hydrophobicity will come in case of HIC, which we had previously discussed. So other than this, we had previously also discussed ion exchange, affinity, gel filtration, etc. So just a quick recap that ion exchange depends on the net charge of the protein and no surface area, etc. Affinity is specific binding pairs like antibody antigen, and then it is independent of protein surface area. Then gel filtration is now what we are discussing. So next is a question, like most of your questions this time are like depending on how much you can understand the concept of your gel filtration chromatography. So here they have given many statements, assertions and reasons. So you have to think whether your A and R are correct first, and then decide whether your reason is correct for your given statement. So, in this case, if you see, your assertion is that the small molecular weight proteins elute later at a retention time than the larger ones in the gel filtration chromatography. So, this is basically true. So, the reason what they have told is that the smaller molecular weight proteins get trapped inside the beads used as stationary phase and takes longer time to get out of the beads. That is what we discussed. So this is also true and it is also the correct explanation. So why this happens is because your stationary phase is porous in nature and it is made up of porous beads which are made up of sephadex, sepharose and superdex, and then these beads contain pores of defined sizes. So you can use your beads based upon whatever is your requirement. You can order different size of pores, porous beads, so that you can separate particular molecular weight proteins. And if your range is very large, you can go for higher pore size. Or if your range is very narrow, if you want to separate like proteins which are having molecular sizes very close to each other, you can go for uh, lower pore size or the pore sizes within that particular range. So larger proteins, that is, which have high molecular weight, they are too big to enter the pores. They travel around the beads only and take the shorter path and therefore elute first. So small proteins, they are small enough to enter the pores. This means that they spend more time wandering in and out of the pores and their path is much longer and they elute later. So the concept is not about trapping them permanently, but here it is to delay the retention time. So it's not like you might think that what if they enter the pores and then you lose your protein? Your protein doesn't come out if your protein is of smaller size. But no, you will have your illusions later where you will use buffers and you can elute them out from the pores easily. So this is because you have your partitioning into the pores and your it's about the delayed illusion, which will be due to the increased partitioning into the pores. So basically, in your assertion and reasoning here, A is correct and R is the perfect explanation. So your small proteins, pore entry, longer path, delay dilution. Large proteins, excluded from the pores, shorter path, early elution. This is what you have to basically remember. And so the purpose of gel filtration is to separate molecules based on size. Like we discussed, it's very repetitive this time, just bear with me. But so the stationary phase is beads like cephacryl and superdex with pores defined size, with pores of defined size. So the principle is like we discussed, large molecules cannot enter the pores, elute first, small molecules enter the pores, take longer paths, elute later. So here comes now the column volume, the void volume, the illusion volume when you actually perform the column chromatography or the gel filtration in the column. So you have a column where you will have your beads, it will be of a certain bed volume. So here you have something called as partition coefficient. Like in the previous we discussed, based the illusion is because of increased partitioning into the pores. So your partition coefficient or your distribution coefficient, which we also discussed a couple of sessions ago, is given by a volume, given by a formula which has volumes of your void, illusion, etc. So the formula is KD. KD is your distribution coefficient, which is equal to VE minus V naught by VT minus V naught. So here your V naught is your void volume. Void is basically empty space. So it is the volume that is outside the beads. So the molecules too big for the pores will travel only through this void volume, and these molecules elute at V naught, that is earliest possible elution. Then you have something called as VT. So VT is your V naught plus the volume of the liquid inside the pores. So basically it is the total volume. So your void volume plus the volume inside your pores will give you your total volume VT. Then we have something called as illusion volume. So this is the actual volume at which a given analyte elutes. So this is different for different columns and different beads. So then you have to incorporate this. So your distribution coefficient is basically the difference between your illusion volume and void volume divided by the total volume of the column by void volume, because void volume is, as I said, it's the empty space or it is the volume that is outside your beads. So now so your KD can vary between 0 to 1, so depending upon its partitioning into the pores. So if your KD is 0, the molecule is excluded from the pore. So basically your molecule is not entering the pore, so there is no partitioning inside the pore. So there will be no uh, like there won't be any specific partitioning of it going outside and inside. It's completely all together outside. So your molecule is excluded from the pores, so it elutes out at V naught, that is in your void volume. Then if your KD is equal to 1, the molecule is fully included into the pores, and that means it's so small that all your protein has now entered into your pores, and it elutes at VT, that is total volume, because your molecule will now go completely through all the pores, so it will take your total volume. So if your KD is less than 1 but greater than 0, then your molecule has partial access to the pores. Like in the previous question we discussed, there might be partially uh, passing through the pores. Like if the pore size is similar to the protein size, it can go sometimes into the pores. Few of them might go into the void volume. So that time it elutes somewhere between your void volume and your total volume. So why these volumes are important is because you have to know where to collect your fraction. So based on all this knowledge, you will calculate the volume at which your protein of interest or the pure form of your protein will elute out. So you will collect different fractions, and you will know based on these V naught, VT and KD information, you will know which volume will have your protein of interest. So that is the reason this V naught, VT, VE and KD are very important while doing gel filtration chromatography. I hope this is clear. Then if KD is equal to 0, then what happens? So if KD is equal to 0, that means your difference between your uh, illusion volume and void volume divided by the total volume and void volume is basically 0. So when VE, this will, this can also be interpreted as VE minus V0 is equal to 0. So this will become your VE equal to V naught. That is, your illusion volume will become equal to your void volume. That is why your KD is 0. So that is why when your KD is 0, it will elute at V0, because that time your illusion volume is nothing but your void volume. It is same as your void volume. So this means that the analyte is too large to enter the pores and it moves through the shortest path, that is the void volume only. It elutes earliest at the void volume. So you know that your protein did not enter into any kind of pores into the beads, and it has taken the shortest path possible because it is too big. So this is like a table. If your KD is 0, VE equal to V naught. So that means it's a very large protein and it has been excluded from the pores and it will elute out first in your void volume. Then if your KD is less than 1 and greater than 0, that means your V naught, your VE, that is your illusion volume, is also less than your total volume but greater than your void volume, because it is in the middle now. It can partially have an entry into the pores and partially it can go through the void volume. So it is intermediate size and it elutes in between your void volume and total volume. So if your KD is 1, that means it enters through the pores, it has full access. So your illusion volume will become your total volume and it will elute out at the end. So basically, to summarize, large molecules will have KD equal to 0 and will elute at V naught, that is in your void volume in the first itself. And then if the small molecules KD equal to 1, it will elute out at the last in your total volume. Then medium molecules will have intermediary partitioning, so it will have your illusion volume somewhere in between your void volume and total volume. So next is regarding the absorption in case of gel filtration chromatography. So like we know, gel filtration is basically size exclusion chromatography and it separates only by size. So there should not be any kind of adsorption in this whatsoever. So there is no chemical interaction, there is no any kind of bond formation, charge based attachment should not be there. So the stationary phase is made up of porous beads like Cefidex, Supadex, and Safacryl. The molecules travel through the column depending on how much they can enter the pores. So the large molecules are excluded from the pores, travel faster, elute earlier. Small molecules enter more pores, travel slower, elute later. No chemical reaction, ionic, hydrophobic, or affinity is seen in case of gel filtration. Theoretically, nothing of this sort should occur. So your analyte with KD is equal to 0 is VE equal to V naught. So these analytes will completely be excluded from the column. And if your analyte KD equal to 1, so VE is equal to V naught plus VI. That is a different way of representing it. It's basically a total volume. So these analytes will be completely into the pores, so it will come out at VT. So in case of KD less than 1, this situation, sometimes it can suggest that your analyte has been absorbed, because your KD should be between your 0 to 1. If it is surpassing 1, that means it might have some sort of adsorption or it is showing some sort of interaction with your column matrix. So theoretically, adsorption should not occur. Why it should not occur is your sec resins, that is your size exclusion chromatography resins, are chemically modified to be inert and hydrophilic. So materials that are used, they are made in such a way that they do not interact with your proteins or other biomolecules. So they are usually cross-linked with dextrin, agarose, and polyacrylamide, which will not interact with it. So it will not have any kind of, it should not have any kind of adsorption. So the surfaces are basically passivated. That means they do not have any kind of active reactions with the sample. So they are passive and so do not bind to the protein. This ensures that the separation depends solely on the molecular size, not on the charge or hydrophobicity. But what happens? The reality in the labs. So when you actually perform a gel filtration chromatography, you will see that in some cases this is not the thing that is happening. So sometimes what happens is adsorption does happen, but that's a problem, not with the principle. So that this is not part of the gel filtration principle. It is part of it is some other issue with the matrix or anything else. So this should not be included as a key point in the principle of gel filtration, because absorption should not take place. So what happens sometimes in practically when you're doing, proteins may stick if the resin is not fully inert. Like we discussed, the resins are passivated, they are made inert so that they don't interact. But if your quality of your resins is not very good, and or they are like somehow lost the capacity to be completely passive, and they're not fully properly inactivated or made inert, so that time they might show some interaction with your proteins and they will have some kind of adsorption. So, how to fix it? So, you can use additives like salts, detergents, or BSA to block the non specific binding. So, like you block in case of your Western blot or in case of your any other antibody related studies or experiments like immunofluorescence, IHC, etc. etc. So, you actually have something called as blocking, where you use either BSA or skimmed milk in case of Western blot to block the other background areas of your uh, membrane or of your tissue where your antibody might bind accidentally. So to avoid that noise of background, we will block it. So in the same way, you can also use blocking reagents like BSA to block non-specific binding in your column in the beads, or you can use detergents or salts which will reduce the interactions between your protein and the beads. So this is a small table where you can see in case of sec, it is only size and pore and there should be no adsorption ideally. In case of ion exchange, since it is charge based interaction, you should have strong adsorption, otherwise your chromatography will not function. In case of HIC also, it is based on hydrophobic interactions. So here also we need hydrophobic adsorption in the patches. And in case of affinity, basically it's based on ligand specific binding. So you definitely need adsorption. So SEC is basically the only one where you do not need adsorption or adsorption does not play a role in separation. So in ideal scenario, in case of gel filtration, um, that adsorption should not take place and the separation should be based on only size of the molecules. So the partition coefficient Kd is crucial indicator of this process, and with values between 0 to 1 indicating the size based partitioning. If the Kd is greater than 1, that means it might suggest that it has adsorption in the column. So this demonstrates that the separation is no longer purely based on the size. There is some kind of interaction or adsorption going on, which is affecting your gel filtration process. So this is how adsorption can trouble your chromatography in case of gel filtration. So adsorption or non-specific binding of an analyte to the column matrix interferes with this ideal size-based separation and changes the effectiveness of it. So, how to prevent it? To maintain separation by size alone, gel filtration media are designed to be as inert as possible to prevent adsorption. In practice, however, some unwanted chemical interactions can still occur, such as electrostatic or hydrophobic. To minimize these specific, there are several strategies that can be employed. So, use an appropriate mobile phase, that is your eluent. Have higher ionic strength buffers, often used to disrupt weak electrostatic or van der Waals interactions between proteins and column matrix. And mild detergents can be used to the mobile phase to reduce hydrophobic interactions. So also it's important to choose the right column matrix, because some stationary phase materials are more prone to non-specific interactions than others. So make sure that you go through all the matrix, all types of matrix, and for your particular protein or sample, which matrix is most suitable. So for example, some silica based matrices have hydrophobic surfaces, making them unsuitable for separating proteins unless they are coated to have some kind of hydrophilic surface. So you can do such kind of alterations in your matrix or in your buffers to avoid this kind of adsorption based problems. So next is again an assertion and a reason. So the assertion given here is a denatured protein has lesser retention time in the gel filtration column compared to its native state. So this is true. A denatured protein will have lesser retention time. So in gel filtration, proteins are separated based on the hydrodynamic radius or the Stokes radius rather than the molecular weight. So till now we were saying molecular weight. So it's basically implied that if you have a high molecular weight, the size will be more. But what the exact principle is hydrodynamic radius. So a native protein is usually compact and will be folded and will be in its like 3D structure or in a globular form, and it will be very tiny. So this means it can enter to more pores and take a longer time in the stationary phase, which leads to a longer retention time, and this elutes later. But when a protein is denatured, it unfolds. The folded form of the protein, it's like for example a handkerchief. You have a big square handkerchief. If you fold it to put it in your pocket, you make it small, you make it compact so that it can enter your pocket. So that is the native form of the protein which can enter into the pore, because now it is folded. But once you have some kind of denaturing agent which will open up. So if you open your handkerchief it and try to put it directly in your pocket, it won't enter because it's too big for your pocket. But it's still the same handkerchief which is now unfolded. In the same way, your unfolded protein will also have an extended chain. It will be in an extended chain form, and the hydrodynamic radius of it increases. So therefore larger radius, even though both are of same molecular size, remember it's the same protein in the native form. Also, if it's like for example a 50 kilodalton protein, it is still a 50 kilodalton protein. If it's unfolded also, it is still a 50 kilodalton protein, but the shape has changed and the hydrodynamic radius has changed. So that is the reason that larger radius equals to fewer pores are available for its entry, and it is excluded earlier, and it has shorter retention times, and it elutes first. Then the reason that they had given here is the protein denaturation results in decrease in hydrodynamic surface area. So this is opposite. So the protein denaturation increases the hydrodynamic radius. So this is false. And the denaturation increases, not decreases, the hydrodynamic surface area. So a compact globular protein becomes extended and becomes a long loose chain. So the larger surface area of the protein is exposed to the solvent, and thus instead of shrinking, the denatured protein behaves like a larger particle now in the chromatography, and it takes the path outside the pores. So basically, in gel filtration, denatured proteins behave as though they are bigger and elute earlier than their native compact counterparts. Hope this is clear. Is anybody still there? Yeah, okay. Like, do you guys have any doubts up until now? If you have doubts, you can ask me right now. We can take like a couple of minutes break and then continue the remaining session. Anybody, any doubt?
Should I ask?
Yeah, yeah, please ask.
Yeah. Actually, the part we discussed with the the
Yeah.
KD that is greater than 1. Yeah, we discussed the KD greater than 1.
Hmm.
The, whether the conclusion is that the analyte adsorbed to the column matrix, that is, whether the adsorption phenomenon is taking place when the KD value is greater than 1. Can you clarify that, ma'am?
Yeah, so basically your KD should be between 0 to 1 in principle of your gel
Yes.
filtration. It should not be more than 1.
Yes, ma'am.
But if your KD value is being more than 1, that means it is getting adsorbed. That is why the KD is more. KD is what basically, if you calculate, it's your difference between your illusion volume and void volume by difference between your total volume and void volume. So if your illusion volume is much higher than your void volume, and even after dividing it with your total volume, if still your KD is showing above 1, that
Mm.
means your protein is stuck inside. So it can't come out even if your total volume. So your total volume means what? Whatever, like if your suppose your column is say 5 ml column. If you add 5 ml of your eluent buffer, your entire thing in your column should come out, for example. I'm just saying a simplified
Okay.
version. So it has to come out technically, say. But even after your total volume of your column is run out, like every last drop from your top of the column has come to the bottom, but still your protein has not come out in your volume. That means it is still in the column. That means there is some kind of adsorption that has been taken place. So that is why your KD is more.
Okay, ma'am. Okay,
Okay.
I don't know whether it's a blunder. How we know that, ma'am? All the proteins have come out of the column at the end of the process.
So
How
that
will
you
we?
have to check your volume. Like you can do anything. You
Oh,
can do either protein estimation, or you can, run your gel, the different volumes which you have collected. You can run in your gel, stain your gel, and check the particular molecular size of your protein. Or else you, if you want like very specific, like if you want beta actin only, that means then you can further continue it to Western blot and add your beta actin antibody and check whether it has come in your volume or not.
oh, so we have to go through a long process to determine that whether all the given proteins have come out or not, right, ma'am?
Yeah, yeah. So basically, like now you have it all like digitalized. So basically, you will get to know that in which fraction, where it is, your instrument will calculate and tell you. But confirmation step, you have to do downstream processing and find out whether you have actually collected your protein or not.
Okay, thanks, ma'am.
Yeah. Uh, Good. Anybody else? Any doubt? Yeah, no more doubts. Okay, I'll just take like 2 minutes break and then I'll be back. So in the meanwhile, if you guys have doubt, you can just post it in the chat box here. Okay. It is what? It is 3:58. I'll be back by 4 exactly. So I will be back by 4 o'clock exactly. You guys also can take like couple of minutes break. Yeah, so I guess there are no more doubts, so we can continue. I hope I'm audible and my screen is visible. Okay, so where were we? Yeah, so this was the last one we discussed. So, yeah, so basically, you have to remember this KD, VE, V naught, and VT to understand anything what is going on when you run it. If you are like, for example, how to check which fraction has your protein, excuse me, or how to know like at which fraction it will dilute out. So you have to have all these information. So now coming to retention time versus KD. So what is the difference? So retention time is something, the time amount of time your protein takes in your column to elute out, and KD is something which affects your retention time like we discussed before. It's the partitioning into the pores. So the more pores a molecule explores, the longer its path and it later comes out. That means if protein is small, it will try to it will basically enter all the pores possible in its path, and it will take a much longer route and it will come out in the end when you're eluting it. So if KD is 1, that means it is of the smallest molecules and it is completely able to go into the pores. So it can fully access your pores and it has the highest retention time. So it will elute out at the last when you elute out the total volume of your column. So that's why your VE will be equal to VT. But if your KD is like half, sorry, if it's half, that means it is in the middle. So now it will have partial pore entry and partially into the gaps or into the void volume. So it will have an intermediary retention time. So basically, it will be in between your total volume and your uh, void volume. So if your KD is 0, then it's a largest molecule and it will elute out first because it will have no chance to enter the pore, and its elution volume will be equal to its void volume. So it is the lowest retention time and it will elute out first. If your KD is 0.25, that means it is larger than your protein which is of intermediary, but still not fully excluded. So it will have an retention time earlier than your zero point 0.4 but later than 0. So this is like a simplified table for it. So if it is 0, it's very large. Elution volume will be your void volume, lowest retention time and fastest. If it's 0.25, as it increases, your protein size is decreasing and your elution volume is also increasing. So your retention time will also increase. So if it's 0.25, it's still a larger protein but not the largest in your sample. So it will have between void volume and total volume, and it is a low moderate retention time and it will come out second in this set of KD values. And zero point 0.5 is medium or intermediary. It will have exactly in between your VT and V naught, and it is moderate and it will come out after 2.5, 0.25. And if it's 1, it's the smallest. It will take the longest route, so therefore highest retention time. Its VE is equal to VT and it will elute out at the end. So next is the materials which we use for the resins or the beads. Like we discussed, there are Cephidex, Cephacryl, uh, Superdex, etc. So like I said, you can also alter the pore sizes. Let me just show you this picture. So you can also get different pore sizes in your beads depending on the type that is used. So that is what is here, the G25, G50, G75, G100, etc. So what is Cefidex G100? So Cefidex is basically, first of all, a cross-linked dextrin beans, and it is used in sec. And there are different grades of Cefidex. So G is your grade 25, grade 50, grade 75, and these are designed for different fractionation ranges, meaning different molecular weights of different proteins and polymers that can effectively it can effectively separate. Like I also told you guys, you can choose your material depending on the range of the molecular weight your proteins are in the sample. So fractionation range of your Cefidex G100 here specifically, it has a range of 4,000 to 1,50,000 Daltons. So anything in between 4,000 and 1,50,000 Daltons, you can use G100 and easily separate them. So molecules greater than 1,50,000 Daltons are basically excluded because they won't enter the pores, and molecules less than 4,000 Daltons can penetrate completely inside and will come out at the end. So only those within your 4,000 and 1,50,000 are separated effectively. Because why? Because like if you have different protein sizes in between your 4,000, like say example you have 5,000, 10,000, 20,000, 30,000. So based on their size and the calculations, you can know that at a particular volume you can easily separate it and collect it. But if it's less than 4,000, it can't differentiate. Anything less than 4,000 can enter into the pore. So you can't separate anything between 1,000 and 4,000. Everything will come out at the total volume. So there will be no difference. You can only know that they are less than 4,000. And same way, if it is above 1,50,000, you can just know they are above 1,50,000. You cannot know whether they are 1,70,000 or 1,80,000 or 2 lakhs. Everything will be eluted out first. Everything above 1,50,000 will be eluted out together in the beginning itself. So if you have to have the proper separation, you will choose proteins for G100 in between 4,000 and 1,50,000, where they can effectively separated and resolved. Okay. Then these are some other resins or materials that are used. So Cefidex is your dextrin resin. For agarose, you have Cephalose, and your cefacryl is basically your acrylamide, your allyl dextrin bis acrylamide. So using these, because like they said, it is inert and they are pacified and they have like least interactions, almost least interactions with your proteins. So you have different grades. G10 ranges 0 to 700, G25 ranges 1,000 to 5,000, G50 ranges 1,500 to 30,000, G100 ranges 40 to 4,000 to 1 lakh 50,000, and G200 is 5,000 to 6 lakhs. Uh, then you have Cephalose, here you have names like 6B, 4B, CL4B, CL2B, etc. So these are their particular ranges where you can separate your proteins. And then for cefacryl, you have like S200, S300, S400, etc. So some other advantages of these are like dextrin is, that is basically Cefidex is, it has smaller fractionation ranges and they are good for desalting expanded forms and require low pressure and hydrostatic heads. Then agarose or cephalose is good for larger molecular weights. You can see they are higher. You can go till 20, 40 lakh Daltons also. So they are good for larger molecular size and their cross-linked forms are more robust, but they must be always moist and kept wet and not allowed to dry. So if your resin or your column has dried, you cannot reuse it properly. Then you have your cefacryl, which is not biodegradable, but it is mechanically robust. And here also you can go to very large molecular weights. And this also must be kept wet and not allowed to dry out. So these are few of the examples of your column beads used. Then coming to the distribution coefficient, What exactly is your KD in case of gel filtration? So, in gel filtration, as you know, the illusion of a molecule depends on how much it can penetrate into the pores of the beads. So, your KD is given by your VE minus V naught by VI. Here, your VI is basically your V naught, it's your internal pore volume. So your V naught is your void volume, your VT, that is your total volume, is V naught plus VI, and your VI is internal pore volume. So VE is your elution volume. So like we discussed previously, your KD is 0, KD is 1, KD could be less than 1 and more than 0 and not greater than 1. So, coming to this, how you can relate your molecular weight and your partition coefficient. So, in case of gel filtration, the separation is based on size, that is your hydrodynamic radius to be particular. So proteins are globular, mostly your native forms are globular approximately. So the radius relates to the molecular weight by something of a proportionality of your molecular weight to the power of 1 by 3. So radius is directly proportional to the molecular weight to the power 1 by 3 because they are in native forms and they are not exactly how your molecular weight is. So your larger molecular proteins have a bigger radius excluded from the pores, have smaller KD. Smaller molecular weight proteins have smaller radius, enter the pores and have larger KD. So then we use it in terms of log molecular weight. That is because the relationship between the molecular weight and hydrodynamic radius is not exactly linear. It is somewhat sigmoidal. But at a particular given range, you can take it to be linear. So when you take a logarithm of your molecular weight, the relationship between the log and the KD becomes linear. So when it is linear, you can use it in the fractionation range and you can use a standard, you can use calibration curves and you can delineate your unknown molecular weight. But if it is not linear, it becomes difficult. So that's why we take a logarithm of molecular weight so that the curve becomes linear. So that's why calibration curves in gel filtration are always plotted as log molecular weight versus KD. Then practical application during column calibration, you run your standard proteins of known molecular weight and then you plot their KD versus log molecular. It's like your protein estimation. You have your standards, you will plot a graph, you will have a linear line and then you get a straight line and using that straight line you can plot your unknown. So then when you run an unknown protein and measure the illusion volume, calculate the KD, project on the calibration curve, you can read the molecular weight from the straight line. So that is the reason if you take log molecular weight, you can get a straight line which you can use to estimate the uh, molecular weight of the unknown. So the linear relationship between the log molecular weight and KD is the basis for using gel filtration chromatography as molecular weight estimation tool. So a plot of KD versus log for a series of known molecular weight standards will produce a graph that is linear over a particular range. So you can see here the graph if you have taken. If you have not taken, if you see it kind of goes like a sigmoidal, but in a particular given range you can see it is linear. So you can use that range to find out your unknown. So standards are basically a set of proteins with known molecular weights and are run through the gel filtration column and their elution volumes are determined. Then that is they have particular illusion volumes which is also known. Then plotting this, the KD values are plotted against the logarithm corresponding to the molecular weight to get a selectivity curve. So when an unknown protein is run through the same column, its illusion volume and KD value can be used to calibrate the curve and determine its unknown molecular weight. So if you know your KD, you can get your molecular weight. So that is the reason you have your log molecular weight and KD, which will give you a selective linear plot. So next, so I think till now we have like repeated the KD and the principle of everything. So I guess the last few questions you guys can answer. So I hope you guys are still there. Yeah. So you guys can turn on your mic and answer the couple of questions left because they are just assertion and reasons. So the next question was, the smaller sized proteins have larger KD values. The smaller, and the reason is the smaller sized proteins have to go through the pores of the beads. So, which is correct according to you guys? Can anybody answer? Are both true and is R the correct explanation? Or are both true and R is not the correct explanation? Or is A true, R false, A false, R true? A, B, C, D. Which is the option? Anybody, just based on whatever you have understood till now, you can answer this question. Anyone?
The D option, A is false, R is false.
Okay, somebody is saying it is C. A is true, R is false. Is it that?
Not D.
D. A is false, R is true.
Yeah,
Okay. Anybody else
it's false.
has?
Both are false.
Oh, sorry. A is also false, R is also false. Okay. Anybody else? Any other answer?
Sorry, ma'am. A is false and R is true. I think so.
Okay. A is false, R is true. But I don't see any option like that, no?
Option. Yes. Sorry.
Okay. Anyone else? Any other answer?
Both are correct.
Okay. Okay. Somebody said both are correct. So both are correct. Again, we have two options, A and B. Which is your answer, A or B? Yeah.
It's B.
B. So you are saying both A and R are true, and R is the correct explanation of A.
Yes, ma'am.
Okay. So does anyone have any other answer? Okay. Yeah. So A is correct and R is also correct, and it is true. So says that the smaller sized proteins have greater KD values. We discussed this, that if your protein size is very small or smallest, your KD value is 1. 1 is maximum. So that means if the small size is small, KD is very high. So someone said A was false. I hope it's clear now. So, yeah, so the small proteins can diffuse more into the internal pores, and this increases the path length and they take longer to elute. So, therefore, their illusion volume is also high, giving them a larger KD. And R is also correct because, of course, if the size is small, the proteins have to go through the pores of the beads. So, the resin beads in the gel filtration are porous. The small molecules can enter these pores while big molecules cannot. So, the more the protein enters the pores, the higher the KD value becomes. So, therefore, the reason is also correct, the assertion is also correct, and the reason is correct for the assertion. Next question. Protein is treated with different increasing concentrations of urea that gives three different protein based on their structure. So the native protein without urea, partially folded protein with 4 molar urea, and unfolded protein with 8 molar urea. So if we mix three proteins after the urea treatment and run on the gel filtration, which of the following will elute out first? This also we discussed. So somebody can give the answer. Which one will elute out first? We discussed this just now in the previous questions. Native form, denatured form, unfolded form.
Option A.
Okay, so somebody is saying partially unfolded and unfolded proteins elutes together with before native protein. Okay, any other answer?
Option D, no?
Option?
Unfolded protein.
Unfolded protein.
Unfolded protein, option D.
Okay, okay. Next, any other answer? Anybody has any different answer?
And option B, native protein.
Native protein. Okay. Next, anybody wants to say C? Or anybody wants to like support somebody who's saying the correct answer, if you know. Okay, so we had discussed this. So your unfolded protein will come out first. That is nothing but your denatured protein. So if it is denatured, I gave you the handkerchief example, na. If it's folded, it is small, it will go into the pores, it will come at the last. If it is unfolded, it is big, it won't go into the pores, so it will pass from outside the beads. It will go into the void volume. Okay, I hope it is clear. So the key principle is the hydrodynamic radius. So larger proteins. So here your unfolded will be the largest form. Then will come your partially folded. Then will come your native protein. So here your native protein is compact and globular. It has small hydrodynamic radius. Your partially unfolded protein will have intermediary expansion. It will be half folded, half closed. So that will have larger radius than native, but your completely unfolded protein will have an extended conformation and will have the largest size or largest hydrodynamic radius. So anything, it is little confusing, I understand, because small ones go to the pore, you might think it will come out first, but no, if it goes to the pore, remember it has to goes to several hundred thousands of pores. So instead of going through those many pores, the unfolded protein will just come out in the gaps. Gaps are less compared, I mean, the gaps are much easier to flow out, right? When you flow the liquid. Like imagine you're having uh, like a straw, a big straw, or like a big glass which is cut at the bottom, okay, which has a tap at the bottom. Your column is basically that only, right? You have a cylinder and a tap at the bottom. So you put marbles inside it and then you pour some buffer, and that marbles have pores, for example, or if it's like your sponge balls, they will absorb the water, right? So when you pour water, the water which goes into the balls will come out later, right? The water which goes between the balls will come out first. So same way, your largest size will come out without entering inside your uh, beads, that is your balls. But if it is small, it will go inside your sponge ball, that is your beads in here, and it will come very slowly outside because it has to now go through every bead, every pore from the beginning to the end. So just remember, if it is large size, it will come out first. If it is small size, it will come out in the end. Okay, so your unfolded protein is biggest in size and will elute out first, and your partially unfolded will elute in the between, and your native protein, which is most compact, will come out in the end because it will go through all the pores in your beads. I hope it is clear. Do you guys have, if you have doubts still, like you can ask me, I can maybe make you understand better if I know what exactly is confusing. Does anyone have any doubt? Okay, so we can go to the last question. So the small, there is again a assertion and a reason. The small molecular weight proteins elute at a later retention time than the large molecules, which than the larger ones in the gel filtration. So they are saying small molecular proteins elute at a later retention time than the large ones in the column. Reason is the larger molecular weight proteins get trapped inside the beads use their stationary phase, and take longer time to get out. Be very careful in reading both the sentences. Don't get confused. So, which option is correct here? Is A correct? R correct?
Option C, ma'am.
Okay. Somebody said option C, A is true, R is false. Any other answer? Anybody else? Okay. So the answer is A is correct, R is incorrect because they themselves are saying the opposite sentences in both. So A is correct because in gel filtration chromatography, small molecules and proteins elute later because they have a large retention time and they can pass through all the pores in the column in the stationary phase and take the longest path. But R is incorrect because large molecules don't get trapped. Large molecules can freely flow in between the beads because they can't enter the beads. They will just flow out in the initial void volume itself. So, in fact, the opposite is true that the large volumes are excluded from the pores, they cannot enter. So, they can travel only through the interstitial. Interstitial is in between the beads, the gaps, the void, and elute out earlier at the void volume. Okay, so I hope it is clear. I know it is a little bit confusing, but if you can just, remember the key points here. Yeah, if you can remember this key points perfectly, and if you remember the concept of how which molecules can enter the pores and which cannot enter the pores, what happens if it cannot enter the pore, it will be a little bit easier. Just take some time, understand the concept, read the PPT, go through the PDF, watch some videos if you can. There might be some animated videos of how proteins go through. It will be easier for you to visualize and understand it. Okay, so I think it is done. So, shall we end the session or do you guys have any doubts? Any more doubts? Anybody?
Ma'am, have I doubt, ma'am?
Yeah, yeah. Please tell me.
Ma'am, with this filtration chromatography, can we know the molecular weight?
Yeah, you can know the molecular weight because you have to run a standard. So, in the standard, you will have some proteins of whose molecular weights you will already know. Like you will have albumin or trypsin or chymotrypsin. So, these are all known molecular weight proteins. So, when you run that, you will know in which fraction each molecular weight is coming. Then, when you later run your sample, if your sample also comes in that similar volume, based on your retention time and your KD value, you can calculate it. That's what I showed the graph na, between your log molecular weight and retention time, KD value. So when
Oh,
you,
okay.
yeah, so when you do your standard, you will get a linear line in that graph. And then when you run your unknown molecule based on the illusion volume or your KD value, you can just uh, put that in value in your graph and you can just see at which molecular weight if that is when you're coming. Okay. Okay, anybody else, any other doubt? Okay, I'll just wait for a couple of minutes. If anybody has any doubt, you can ask me. The rest can leave. We can end the session. Thank you for joining. Okay, I think I can end the call now. Bye. Bye, guys.